Hello. The lecture of today is will be on bioprocessing, and we will talk a bit about the basic things about it. We will go through the concept of a bioreactor. We will see different kind of bioreactors. And in the end, we will see how to model a bioreactor. So, okay. So let's start from the base. When we talk about bioprocessing, we talk about the act of produces something from cells that can be, for example, human cells, bacteria cells, or other kind of cells. And through this, we can have a very complex thing, as for example, the axines, enzymes, etc. One of the simplest example to understand how this works is a think about how we make bread. Indeed, when we make bread, we have three things. We have the flour that is made of sugar, basically. We have the yeast, and we have the water. And in this case, of course, the living cell is the yeast. And what happens when we want to make the yeast? Basically, the yeast eat the sugar that is in the flour to produce some gas that let the dough grow. And in this case, the gas can be considered as a bioproduces product. And one of the most important product that we got through this kind of process in the last 10 years was the vaccine that was produced in 2020, so during the COVID pandemic. And in this case, we are talking about this vaccine, this vaccine. Okay. In the vaccine, Nowak vaccine, we have two things. We have an adjuvant matrix that helps to stimulate the immune system in the human body, but we also have this protein that is called the spike. Basically, yeah, which is this spike protein? What is this spike protein? Like in the coronavirus, we have the virus that looks like that, more or less. And the spike protein are here. And their role is to bind with the cell receptor to allow the virus to get into the cell. And for this, when like it was necessary to find a way to block this kind of virus, the first thing that the company tried to do was to find a way to produce some antibodies that can attack this kind of molecule. And how did they do this? Basically, the COVID spike protein was sequenced in 2020, so we were able to write the instruction that was needed to build this kind to teach to the cell how to build the is. And what the company did is to take this sequence, so this instruction, put it in cells, in particular in insect cells, and allow it to grow inside the bioreactor to produce the spike protein. But we saw that the spike protein was sequenced in 2020. It means that from that point we were able to build it in a vial. But why companies choose to use the bioreactor in this case? The answers to this question are three. Can be three. The first one is that at the time we need to produce a lot of this spike protein, so the best way is to find a way to produce it in a continuous way, so to have a high production of the is. The second reason was that this protein was supposed to be put in a vaccine, so it has to be as more safe as possible. And if we run a process like that in a bioreactor, we have the chance to do this in an environment that is sterile. So, like the protein that comes out from here has more chance to be well-made, stable, and so more safe for the people. And the third reason was biological, because the spike protein looks like the head. So as we can see, it's a complex molecules. So we can see all these course bindings etc. here. So it's not a long chain of amino acid that we can build in a vial, for example. And there is also another important thing to stress about is that if we miss something in the 3D structure, basically this the protein that we can have can be not functional. So the vaccine will be not effective. And so the company chose to rely on bioreactor because in this case the cells were the only way through we can obtain a molecule that is fully compatible with the living system under the biological point of view, because the cells has all the molecules, all the enzymes that are needed to build a structure like the head. That is very complex. So let's pass to talk a bit about the bioreactors. So, of course, like as I said, when we have to use the cells to produce something, we just do make the culture inside the bioreactor. Since we can have the different kind of cells, the different kind of different kind of reactions, not all the bioreactors are built in the same way. In particular, the picture that I'm showing you now is a CSTR. CSTR stands for Continuous Sterile Tank Bioreactor, and it is one of the simplest kind of bioreactor that we can have. So, as we can see, we have a tank here. So, for sure, we have an inflow and an outflow. Like the cell, the substrate, and all the nutrients that we need for the reaction are the air, so are inside the tank. And we can have also, if it's required, a certain inflow concentration of the substrate or of the biomass, etc. And then we have also the sensor and the controller, of course, to check if, to check what is going on inside the bioreactor, and to change the feed structure if and the future properties if it's necessary. But like the most important thing for the CSTR is the fan that is used to steer the whole ocean inside the tank. In this case, it is a mechanical steerer, so it allows to have homogeneous properties inside the bioreactor. But this kind of bioreactor could not be the most the best choice. For example, if we are in the presence of cells that are sensible to the shear stress, because it is a consequence of mechanical steering. So in some cases, we can have the different kind of bioreactor as the airlift bioreactor. The difference between this and the CSTR is that in this case, the steering is not given by the fan, basically, but it's given by the flow of gas that is in the bottom of the bioreactor. Because in this case, like when there is a flow from the bottom of the bioreactor, we have here in this is the zone the creation of some bubble of air, and this allows to locally decrease the density of the solution here, because the air has the density that is lower than the water, and this push the liquid to go up. Sorry. So what we have here is that thanks to the formation of the bubble, the liquids go to the top, up to here, where there is a flow out of the gas. So we have that the number of bubble is the decrease. So the density of the solution here is high. So the liquid tend to go down. And in this way, we have a recirculation of the liquid without having any mechanical stirring. And this kind of structure can be useful for example in the presence of all the cells that are sensitive to mechanical stress, as for example the human cells. There is also another kind of bioreactor, that is this one. This is called the fixed bed bioreactor. The fixed bed bioreactor is made in this way. So we have the tank, and inside we have a sort of bed that is a solid structure where the biomass is stick on it. So we have that the flow with all the substrate, nutrient, etc., came and flow through the bed, and so this kind of bioreactor is used for a very slow process, because like the essence of this structure and the chance to create biofilm of biomass allows to have a higher the density of biomass that can be nice if the growth and production process is very slow. But it is not so good for process reaction that need oxygen, because the presence of the solid structure behind the biomass and the formation of the biofilm on this structure is an obstacle for the diffusion of the oxygen through from the flow that is flowing through the bed and the cell, the M cell. So like this kind of bioreactor is used mostly for process where we don't need the oxygen. Okay, so now we pass on how to, like we will see how to model a bioreactor. So what we have to do to describe what is happening inside the bioreactor. The first things that we have to do is to recognize three things that are the system, the surrounding, and the boundary. the system is the part of the process where we are focusing on. So for the CSTR, that is look like that. So we have the fan. So we have a certain inflow, a certain outflow. Okay, then we can have a concentration, temperature, etc., and a concentration and the temperature of out. So in this case, the system is here. So it's like all the things that are inside the tank, because it's the place where the reaction happens. While for the surrounding is like all the things with which the system can interact. For example, in the case of this CSTR, can be the hair, like around the tank, or if we have it like a jacket to cool down the reactors, and so on. And in the end, we have the boundary that in this case are the wall of the CSTR, and it is basically the surface that separates the system from the surroundings, and is the surface through which we have the flux of mass, the flux of heat, and so on. So, like before starting with the balance, we can say that all the balance are aid on this concept, so that the accumulation, that is basically the like how much of a quantity we have in a system for unit of time. So like the T is equal to how much enter into the system, so the input, minus how much of such quantity goes out from the system, so minus out, and plus minus at a term that is called the generation. This term is the term that we saw in all the previous lecture, and it describes basically like how much of that quantity is created or consumed by the reaction inside the system. So let's start from the mass balance. So, okay, we will have accumulation is equal to input minus output plus minus generation or consumption. So it's a plus, but it's a plus if we are generating. It's a minus if we are consuming the species inside the system. So for the mass balance, we can write two equation: one on the whole flow and one on the single species. For the whole flow, we can say that the variance of the mass over time in the system is equal to the total mass in input, sorry, minus the total mass in output. What does it means? That like if the mass in input of the system is higher than the mass on the output of the system, the accumulation of mass will be positive. So we have an increase of mass of the total mass inside the bioreactor. While if the mass in output is bigger than the mass in input, we will have the decrease in the total mass inside the bioreactor. But we can write this also for the single species. Like in this case, for example, the component he can be the substrate, the biomass, etc. And when we have to look like at what it's happening inside the bioreactor, we have to write one mass balance equation for each component we have. So in this case, so we have that for the component mass balance, we have that the volume times the concentration of the single species inside the bioreactor per unit of the time. Of course, like this kind of concentration can be expressed in terms of mole or in terms of grams, is equal to the flow in input times the concentration in input of the component. So concentration of the component in input minus the flow in output times the concentration of the species in output plus the reaction term. So we have input, output, and now we have the reaction term, that is the reaction rate per unit of volume times the volume. So like in this case, as we saw during the previous lecture, the reaction rate can be positive or negative. So when it is positive, we have the generation. When it's negative, we have the consumption. So like this is an example for the biomass. So if like we have an inflow in the bioreactor of the amount of the biomass in inflow of the bioreactor, we will have something like that, so that the accumulation of biomass over time in the system is equal to the volumetric flow rate in input times the concentration of the biomass in input minus the outflow times the concentration of the biomass that we have inside the bioreactor at a specific time t, plus the growth rate constant times x times v, because like the concentration that we are considering here are per unit of volume. So like to like have like a homogeneous the distribution of a unit of measure. If we have v here, we have to be here also. We have to have also v here. And yeah, so this is like about this is all about the mass balance. So we just add to what we knew, like the input and the output term that is connected to the flow that we have through the bioreactor, basically. Okay, now we pass to the energy balance. The energy balance describe what happens inside the system in terms of heat and in terms of work, because we know that for example, when we have reactions inside the bioreactor, according to if it is an endothermic bioreaction or an exothermic bioreaction, it can have an effect on the temperature that we have inside the bioreactors. And in particular, when we have an exothermic reaction, we have that we have an increase of the temperature inside the system. When we have endothermic reaction, we have like we can have a reduction of the temperature of the system. And to describe this, we have to write this kind of balance. So what we have is that the variation of the internal energy of the system per unit of time is equal to Q. Q dot. This is like the this can be, for example, the heat that came from cooling system or from the surrounding in the general. So this term can be a plus or a minus, so can be positive or negative according to the effect that this term has to the system. And in particular, like all the terms that increase the amount of heat inside the system are considered as positive, and all the quantity that leads to the decrease on the heat inside the system is considered as negative. So this is like the flow that the thermal flow that we can have from the surrounding. Then we have the work that we can have. For example, if we have some amps inside the like in the structure of the bioreactor. And then we have two terms that are like the this is the term correlated to the enthalpy that we have, correlated to the inflow of mass and the outflow of mass. And if we consider, if we are in the hypothesis of constant flow, so we have that F in, like the inflow rate is equal to the flow rate, to the outflow rate, and we have that the density is constant inside the bioreactor. So we consider like the hypothesis of ideal mixing. We can see that we can say that we can write the balance of heat like that. So we have that the density of the system time the volume of the bioreactor time the heat capacity. That is a properties that describes how good can material store heat times the variation of the temperature over time inside the system is equal to the heat transfer that we have from the surrounding. So it's negative if we are heating, is if we have something that is heating the system, is negative if we have something that is cooling down the system. Plus minus delta HR. This is the variation of enthalpy that is correlated to the reaction. And in particular, the delta H is positive when the reaction is endothermical. So it's like the whole term, the minus delta H is negative when the reaction is endothermical. And this makes sense because it's something that is cooling down our system. And it is like the whole term is positive when the reaction is isothermical. So it means that the delta H term is negative for isothermical reaction. But we have to write this in terms of like per unit of like we have to multiply this for the growth rate, of course, because like this is the variation of enthalpy induced by the reaction that we have times the volume, because like the growth rate is per unit of volume, plus the density of the flow that we have just one the density and one flow, because we are considering the ideal mixing hypothesis. So the density of the solution inside the tank is the same in all the points of the tank. And we are considering just one F, because we know that the F in the global F in input is equal to the global F in output times the Cp, so the heat capacity of the fluid, times the temperature in input minus the temperature that we have at time t. Of course, if we have to write this kind of I mixed two things. Okay, so we have to like I wrote this, but like we can write in more general way the is if we not consider like the constant flow and the constant the density. So of course we would have a flow in input and a flow in output, and a temperature in input and a temperature in output. Yes, so like if we want to write this for a specific like like for example, of course, if we have the different reaction, we would expect the different like delta H of R, because this is the value that is specific for specific reaction. And if we have, for example, the different fluid in the bioreactor, so I don't know if the broth that we have inside the bioreactor is oil instead of water. What we have is to like of course, the different row, so different the density, but also the different CP, because like both the rho and the CP are physical properties of the solution that we are considering inside the tank of the bioreactor. Okay, so we discussed about the difference between exothermical and endothermical. Okay, so let's pass to the momentum balance. I will just speak about this in a very fast way because like it's a balance that is not that can be not considered when we are doing very basic bioreactors, but like this kind of balance describe how the momentum change inside the system, and so it describe more how the flow flows inside the bioreactor. And for example, like some aspect that can be taken into account by this kind of balance, like as we saw for the mass balance, it describe how the mass, how the global mass or the mass of a specific component change per unit of time. The thermal balance describe in a very simple way how the temperature change inside the bioreactor according to what happens inside the bioreactor and what happens around the bioreactor. In this case, what we have is, for example, the description of the mixing condition inside the bioreactor, and in general how the fluid flow through the bioreactor. For example, in this part, we can have some info about the force that push the fluid to flow, but for example, also the force that obstacle the fluid to flow, as for example the viscosity of the fluid. Okay. So, okay, these are example of the mass balance for the substrate, mass balance for the biomass, and energy balance on the system in a CSTR when we have a constant volume at the steady state, so we have no accumulation. So indeed, this term is zero. And okay, this kind of equation can be really useful for the problem session. Okay, now, like we saw at the start of the lecture, that there are some case in which bioproducing per ODAC is the best way to do this. For example, we saw the complex structure of the spike per protein of the COVID-19 vaccine, and we saw that cells are the only tools that we can use in order to have a 3D structure that can be compatible with the life. So, like that have all the enzymes, all the molecules that we need to have this complex structure, and to have a molecule that is safe for the humans, but that is that like does what we want it does. But like there are some cases in which bioprocessing is not a good idea, at least now. One of these is one of these cases is the production of the vitamin C process. And in particular, in this case, the traditional chemical synthesis process is still the most used alternative by the companies. And this is done by this very long and complex process that is called the process Einstein. And this process was done in the second part of the last century, and it is a process that is highly used by company because it has yields of production of 90%. Which means that the 90% of the substrate that we have is converted into product, which is a very high amount because it's roughly one to one. So it's a very high value. But this kind of process is not so good for the environment and for the workers because it relies on the use of strong bases, strong acids. It needs high temperature, so it is costly, and so like. It is not so good for a lot of reasons, but it is still used under the industrial point of view because it has a very high yield. In the last 10 years, there was the scientist was trying to find a bioprocessing alternative to this, and they get something. In particular, they found a way to produce the vitamin C starting from some engineered bacteria that are the okay, these two names that are very long, and but like even if the process is fine because like it doesn't rely on solvents that are not so good for the environment and for the workers. They like this kind of alternative has a very low yield if it is compared to the traditional synthetic one, because with the traditional synthetic Einstein process, we can have a yield of 90–95% in a few days, while for this alternative, we can have a yield of 60–75% in weeks. So like this could be an obstacle like to meet the need of the company to have a strong production of vitamin C that is at the base of a lot of the drugs. So we have a high demand of this kind of product, and by now we can say that the traditional synthesis, chemical synthesis process is still better in terms of in terms of rate of production of vitamin C when compared to the bioprocessed one, which means that bioprocessing is not can be like bioprocessing in presence of very complex molecule in which the safety is an important thing, as for example the molecule for a vaccine is like the best choice. But when we have like when we are in the presence of not so complex molecule, as for example the vitamin C, it's still like a company choose still to rely on the traditional synthetic process. So, which are, and this will be the last topic, the last part of this lecture. Which are the steps that we can take to improve the yield, for example, in a bioprocess? What we can do is for sure to have a strict control on the critical parameters inside the bioreactor, which like allows us to adjust the feeding strategies in order to have inside the bioreactor always or as long as possible the optimal condition for the bioreactor that we are doing, that for the bioreaction that it's happening inside the bioreactor, but also to improve the digitalization and the automation of bioprocess, especially in terms of data collection and analysis, in order to improve the quality check on the product, even in the case when we don't have an answer for checking that specific properties. So, like this were the way to the steps that is possible to make in order to increase the yield of the bioprocess. And this was the last part for today's lecture. About the problem session. Okay, what we will do is to optimize the protocol for the production of a vaccine molecule in a CSTR. So we will use all the equation that we discussed about during the lecture, doing a specific hypothesis. And yeah, the only things I want to add to the exercise that we have on the website is some data, like some assumption that I did in order to have a comparable result, because I did not specify with which kind of reaction I used. So, of course, I have to specify the enthalpy of the variation of enthalpy due to the reaction. That in my case, like I used for the reaction of cell growth, this is a delta HR, it's not a minus, so attention to this thing, is equal to minus 18,000 joule over grams. So it's per unit of gram. And this is for the cell growth. while for the product growth, so this is for x, this is for p. For the product growth, we have a delta H, a variation of entropy of the reaction equal to minus 11,000 joule over gram. And I consider as a constant the volume of the bioreactor as 1,000 liters. And I considered all the properties correlated to this ocean inside the bioreactor, so the density, the heat capacity, as the one of the water. So like you can find it on books. You can like look for it on the web. And so that's it. Thank you.